Hey folks, in this video we're going to look at inclined planes, basically hills or ramps where something's either sliding or rolling down, and they come up from time to time in AP Physics 1, and we need to know how to analyze them in terms of a free body diagram and Newton's second law, and so that's what I'm here to talk about today. So here we have a box on an inclined plane, and the thing I'll tell you about the box for this particular scenario is that it is at rest. You can expect a variety of inclined plane problems where things are at rest or sliding up the ramp or sliding down the ramp. Maybe there's friction, maybe there's not. Maybe there's a pulley at the top of the plane and there's something hanging off the pulley. There's all sorts of things. So we're going to do free body diagram and then analyze it for Newton's second law. Before we start, I did forget to do this in my classes all last week, but there is an equation for the force of gravity on something, and that is the mass of the object times little g. And so that's something that you will see all over the place. And so, this is the terrestrial weight of something. So if something is on Earth or near Earth, it has a weight equal to its mass times 9.81. So that's going to come into play in just a second. So for a free body diagram, I circle my object, and then I draw it, and then I draw in the forces. So I'm going to draw in the gravity force, and I'm actually going to write it as mg. You can keep writing it as fg, but if you want to cut corners a little bit and write the formula for weight instead of the force of gravity, that's fine. So that's the distance force. There is a surface here, and so whenever we have a surface, we have to consider the two forces that a surface can exert, normal and friction. And so normal is kind of automatic. As long as there's an object in contact with the surface, there's a normal force. And the rule is that it's perpendicular to the surface and away. So it's going to go straight out of the plane. And that means I'm going to draw the normal force off to this side. So it's at an angle. So the force of gravity and the normal force are not in opposite directions. The last one is friction. And since it's at rest, there has to be friction. In other words, if there weren't friction, this box would just slide down the incline because there's nothing holding it there. But because it's at rest, there has to be a force holding it there, and that's friction. Friction is always parallel to the surface, and it opposes the sliding of objects. So the tendency would be for this box to slide down the incline, and so I'm going to put the friction force up and to the left. So the normal force goes out of the inclined plane, and then the friction force, in this case, goes up the inclined plane. So depending what the box is doing, friction can change direction. So before we actually analyze this in terms of Newton's second law, you want to recognize that if there were no friction, the box would accelerate down the incline. And so that is not a force. But I'm going to say, let that direction be the direction of positive acceleration. And you'll see why in just a minute. So I'm going to say, in my reality, and I want you to do this every time you look at an inclined plane, that either up or down the incline is the positive x direction, and then directly away from the incline would be the positive y direction. It's really important that the x direction is on the plane itself. It just is going to make everything in your free body diagram more simple, and it's also going to help reveal what actually causes things to happen on an inclined plane. So I'm going to redraw the free body diagram, and I'm going to draw it over here, and I'm going to set up the positive y-axis and the positive x-axis. So what you want to see is that by drawing my axes like this and then like this, I'm going to rotate my axes. And it's, the object's still on the plane, but I'm just rotating things to simplify my math, but keep the same physics. So that means that the normal force is now vertical. It means that the friction force is now horizontal. That's probably the main reason for doing that, is that it puts two of my three forces along an axis. The other thing it means is my gravity force, if I think about it in terms of this box here, that gravity force is straight down. And if I rotate my axes, then the gravity force rotates with it. And so I'm going to draw my gravity force way out here. So it's going to be down at an angle. So I want to do one last thing for this free body diagram. In this situation, my reality was tilted by an angle equal to theta. Well, in order to make things work out, I then realigned reality. And so I moved my free body diagram by an angle of theta. And so the angle that represents the angle of incline is actually the angle by which the gravity force deviates from the y-axis. And so to kind of further illustrate that, gravity is the thing at an angle here. It's the incline like tilts everything, but that actually makes the gravity force at an angle. And so if I think about this angle here, that means there's a component of gravity that works directly downward and a component of gravity that works directly down the incline in this situation. And that's really important because that ends up showing us what's exactly happening. That force of gravity is actually at an angle in my reality. And so the acceleration would be caused by the component of gravity that is parallel to the plane. If you think about the other forces, it means that that's really the only option, because in this plane, the normal force points straight up out of the plane, and that is 90 degrees away from the surface of the plane. And so it is not possible for the normal force to actually accelerate it, because it would only be served to push up and float the box off the incline, which is not possible. Friction can't accelerate in this situation because it's the natural tendency would be to slide down, and so friction is going to resist that. It's only the fact that the gravity force has a component that goes parallel to the plane that would cause that acceleration. The other way that this makes sense is, if I have a board with a block on it and it's perfectly flat, nothing's going to happen. As I move one side of that board up, it is more likely that box on it is going to slide. And if I continue to increase that incline, the amount of acceleration I would get on that surface is going to increase with it. So by increasing the angle of the incline, I'm actually increasing the component of gravity that is acting along that incline. So that's conceptually one of the more important things about this situation. Okay, so the other thing we're going to do is just Newton's second law, and so this will be kind of quick. There is a net force in the x direction. That's going to be equal to 0 because this object is at rest. And there's a net force in the y direction, and that is equal to 0 because that object is at rest. In the x direction, I have the x component of the weight, and then I have friction. And so this component of the weight is going to be mg sine theta, and that's going to be the positive force minus friction, and that's going to be equal to 0. So I could add friction to both sides. I have a nice equality that I can work with in a variety of settings. For the y direction, it's very similar. The normal force is the upward force, and then the vertical component of the weight is the down force. So mg cosine theta, and that equals 0. The significance of this is that it means the normal force is equal to mg cosine theta. For those of you who have studied trig, you know that the maximum value of a trig function, of a cosine or sine function, is 1. And as the angle increases, the value of cosine decreases. So this means for that all angles of incline, the normal force is less than the weight of the object. So that's like another conceptual thing that comes out of this. The main part of this was to show you the free body diagram, and that is how you want to analyze anything on an incline.